Hello, everybody. Again, a big warm welcome to join me again in the webinar series, How You Can Build Great Solutions with the Microsoft Azure Well Architected Framework. Today, we are already arriving in the fifth episode, in which we are going to have a more deep dive discussion around the pillar of reliability. My name is Jing Liu, and I'm a cloud solution architect working in a partner organization in Microsoft Sweden. Without further ado, let's kick off today's session. We know that your business really relies on access to the systems and data that make you run. Every minute that your customers or your internal teams don't have access to what they need can result in a loss of revenue. And it is our job to make sure that this doesn't happen. Here in this session, you will learn all about the reliability pillar of the Azure Well Architected Framework. This is also the second last pillar that we're going to have a deep dive session in this webinar series. Continue from that brief introduction, we can say that a reliable workload is one that is both resilient and available. The property itself, resiliency, is then the ability of the system to recover from failures and continue to function. Under resiliency, we usually divide it into some further sub-areas, and that's also how I plan to structure today's talk. We'll first have a discussion around high availability. This is basically the ability of the application to continue running in a healthy state without significant downtime. And if you ask, what do you mean by healthy state? We mean that the application is responsive and the users can connect to the application and interact with it. The second area is disaster recovery. This is the ability to recover from rare but major incidents, non-transient wide-scale failures such as service disruption that affects an entire region. And I can mention that one way to think about what's the difference between high availability and disaster recovery is that the DR starts when the impact of a fault it actually goes beyond the ability of the HA design to handle it. And the last one, we also have data backup. And that's also a critical part of resiliency. If the stateless components of application fail, you can always redeploy them. But if data is lost, the system can't really return to a stable state. And that's why data must be backed up, ideally in a different region in case of a region-wide disaster. So after you have set the scene, now let's go a little bit deeper into each one of these sub-properties. And the first one is around high availability. A highly available service is a service that absorbs fluctuations in availability, load, and also temporary failures in dependent services and hardware. So you can basically say that high availability is ultimately about the ability to handle the loss or severe degradation of a component of a system. This might be due to that a VM that's hosting an application going offline because the host itself failed. It could be due to planned maintenance for a system upgrade. It could even be caused by the failure of a service in the cloud. That's why identify the places where your system can fail and then build in the capabilities to handle those failures will ensure that the services you offer to your customers can stay online. High availability of a service typically requires high availability of the components that make up the service. We will aim to remove as much as possible single points of failure. Think of a website that offers an online market to purchase items. The service that's offered to a customer is the ability to list, to buy, and also sell items online. To provide this service, you have multiple components, which are a database, maybe you have web servers, application servers, and so on. And each of these components could actually fail. So you should have to identify how and where your failure points are, and then determine how to address these failure points in your architecture. And then evaluating how your architecture is doing in terms of high availability, that's a critical step. And there are, I would say, 3 steps to evaluate an application for high availability property. The first step is to determine the service level agreement, also known as SLA, for your application. And the second and the third steps are to evaluate the HA capabilities of the application itself and of the dependent applications. In the next couple of slides, we will have a closer look into each one of them. I guess maybe a lot of you are already familiar with the concept SLA. A service level agreement, also known as SLA, this is an agreement between a service provider and a service consumer in which the service provider commits to a standard of service based on measurable metrics and defined responsibilities. SLAs can be strict, legally bound contractual agreements, or they can also be assumed expectations of availability by customers. Service metrics typically focus on service throughput, capacity, and availability, and all of which can be measured in different ways. Regardless of the specific metrics that make up the SLA, failure to meet the SLA can have serious financial ramifications for the service provider. A common component of service agreement is guaranteed financial reimbursement for missed SLAs. So in reality, you will have a set of promised SLAs for your customers. And if you look at from the Azure platform, we also have a set of agreed SLAs that we promise to our users who are using the services provisioned on the platform. If you have a closer look at how SLAs are usually expressed, well, SLAs are typically expressed as cumulative uptime, basically counting the percentage number and the number of nights. As you can see the data illustrated in the table below, for example, an uptime of 99.99 translates to about 5 minutes of total downtime per month. But you should also be aware as you strive for more nights, the cost and complexity to achieve that level of availability also grows. Is it really worth the additional complexity and cost to reach the 5 nights? And that answer depends greatly on the business requirements. And I would like to share some other considerations when you are defining your SLA. First, to achieve 4 nights, meaning the 99.99%, you probably can't rely just on manual intervention to recover from failures. The application itself must be self-diagnosing and self-healing. And beyond 4 nights, it is very challenging to detect outages quickly enough to meet the SLA. You should also think about the time window that your SLA is measured against. The smaller the window, the tighter the tolerances. It probably doesn't make sense to define your SLA in terms of hourly or daily uptime. Identifying SLA is an important first step when determining the high availability capabilities that your architecture will require, and this will help shape the methods you use to make your application highly available. Then let's take a look at how you should evaluate the HA capabilities against your application and the dependent applications. First of all, to evaluate the HA capabilities of your application, you should perform a failure analysis. Focus on identifying single points of failure and critical components that would have a large impact on the application if they were unreachable. For areas that do have redundancy, determine whether the application is capable of detecting error conditions and self-healing. You'll need to carefully evaluate all the different components of your application, including the pieces designed to provide HA functionality, such as the load balancers. Single points of failure will either need to be modified to have HA capabilities integrated, or will need to be replaced with services that can provide HA capabilities. And moving on to the second box, regarding the HA capabilities of dependent applications, you need to understand that not only your application's SLA requirements to your customer, but also the provided SLAs of any resource that your application may depend on. If you're committing an uptime to your customer of 3 nights, but the service the application depends on only has an uptime commitment of 2 nights, so 99%. This could put you at risk of not meeting your SLA to your customers, since that dependent component can become a bottleneck. If a dependent service is unable to provide a sufficient SLA, you need to take some measures. For example, you may need to modify your own SLA for it to match that value. You may need to replace that dependency with an alternative solution, or you need to find other ways to meet your SLA while the dependency is unavailable. Depending on the scenario and the nature of the dependency, failing dependencies can be temporarily worked around with solutions like caches and work queues. The Azure Cloud Platform has been designed to provide high availability throughout all its services. And just like any system, applications may be affected by both hardware and software platform events. The need to design the application architecture to handle failures is critical, and the Azure Cloud Platform provides you with the tools and capabilities to make application highly available. And there are several core concepts when considering HA for your architecture on Azure, and we're going to have a look at them together. The first one, we have the availability sets. In a nutshell, it's about how you want to place your VMs. And to be more specific, the availability sets give you a way to inform Azure that you want to place your VMs, which belong to the same application, and you want them to be distributed to prevent simultaneous impact from hardware failure and scheduled maintenance inside a single data center. And then availability sets, they are made of two additional concepts called the update domains and then the fault domains. And then if we first have a look at the update domain, these are the concepts that ensure that a subset of your application servers, they always remain running when the virtual machine host in the data center require downtime for maintenance. Even though today most updates they can be performed with no impact to the VMs running to them, there are times when this isn't possible. And to ensure that updates don't happen to an entire data center at once, the data center is logically sectioned into the different update domains. And whenever a maintenance event, such as a performance update or maybe a critical security patch that needs to be applied to the host, the update is sequenced through the different update domains. And then another concept that we're going to introduce is the fault domains. While we talked about the update domains, those represent a logical section. The fault domains are really the physical separation of how you're placing your VMs. So basically, these are the different racks that you're going to place the servers on. And they will have independent power, cooling, and networking hardware to support those physical servers located in these different server racks. In the event that the hardware that supports the server rack has become unavailable, let's say maybe you have a power outage, only that particular rack of servers would then be affected by the outage. That's why by placing your VMs in an availability set, your VMs will be automatically spread across multiple fault domains so that in the event of a hardware failure, only part of the VMs will be impacted. So in summary, with availability sets, you can really ensure your application remains online if a high impact maintenance event is required, or maybe you have a hardware failure that occurs. All right, then moving on to another concept, we have availability zones. The availability zones, these are independent physical data center locations within a region that includes their own power, cooling, and networking. And here, by taking availability zones into account when deploying your resources, you can protect the workloads from one level up outages, namely the data center outages, while retaining presence in a particular region. Services like virtual machines, they are zonal services, and they allow you to deploy them to specific zones within a region. And then we also have other services, they are called the zone redundant services. And this will replicate across the availability zones in a specific Azure region. And both types, both the zonal services and zonal redundant services ensure that within an Azure region, there are no single points of failure. I think this diagram explains better what is the scope difference between them. So first we have the availability set, and that is only talking about what's happening inside the data center. So high availability protection from hardware failures between the different racks and the maintenance activity. But if the entire data center goes down, the availability says they're not enough. And that's why we need to move to one step further. In this case, we have high availability protection against loss of the entire data centers. As each zone is physically separated and consists of one and more data centers with independent power, network, and cooling, the applications and data are replicated through zone redundant services as well. Later, when we talk about disaster recovery, we also have the concept called region pairs. If the disaster goes one level up and you have the entire region going down, then you actually need to leverage the other region that is being paired, and we have capabilities such as the geo-redundant storage in Azure Storage, and we also have the Azure Site Recovery to allow you to do that. But this is the next topic we're going to look more closely into. And in this slide, let's take a look at what it really means when you're choosing this different setup and what is Microsoft's guaranteed SLA for our customers. Well, if we go one step back again, even if you're only using one single VM without any redundancy in place, as long as you guarantee that you are using premium storage, Microsoft guarantees that for any single instance VM using premium storage for all disk, you will have a virtual machine connectivity of at least 3 nights, so 99.9% SLA. And if you're using availability sets, meaning that for all the virtual machines that have 2 or more instances deployed in the same availability set, we guarantee that you will have virtual machine connectivity at least one instance at least 99.95% of the time. And that is equivalent to about 20 minutes downtime per month. And then finally, if for all virtual machines that have 2 or more instances deployed across 2 or more availability zones in the same Azure region, we can increase the SLA guarantee to 4 nights, meaning that you will have a downtime of maximum 4.32 minutes per month. Now let's move on to the third quadrant. And here I would like to introduce the 4 different load balancing options today Azure offers. So the purpose of load balancers, they basically manage how network traffic is distributed across the application. And they're very important components in keeping your application resilient to individual component failures and to ensure your application is available to process requests. For applications that don't have service discovery built-in, the load balancers is mandatory for both availability sets and availability zones. And when we look at the 4 different types, we can actually draw a vertical and a horizontal axis on them. So if you first look at what's the difference between the 2 on the left and the 2 on the right, front door and Azure Traffic Managers, these are global load balancers, while the application gateway and the load balancer, they only work on the regional level. And then you can also draw a plane in between. So the top 2, front door and application gateway, these are what we call the level 7 load balancers, while the other 2 below, these are level 4 load balancers. And what they really mean, let me go through them one by one. So the first one, front door. This is the, as you can see, the most powerful tool of them all. This is an application delivery network that provides that global load balancing and site acceleration service for your web applications. As it offers level 7 capabilities for your application, you get to use features such as SLL offload. You can use path-based routing, fast failover, caching, and many more. And you can use this feature to improve performance and high availability of your applications. And then if you look at the Azure Traffic Manager, this is also working on a global level, but this is a DNS-based traffic load balancer that enables you to distribute traffic optimally to services across your different Azure regions, while still providing high availability and responsiveness. Maybe you still remember we went through a scenario when we talk about performance efficiency. In that example, we are using a traffic manager to decide whether the user should be routed to the front end in Australia or West Europe. And we also talk about the different algorithm that you can give to the traffic manager. It can be performance-based, it can be priority-based, or it can be weight-based. But do note that because Traffic Manager is a DNS-based load balancer service, it load balances only at the domain level. And for that reason, it can't really fail over as quickly as front door because of common challenges around DNS caching and also system not really honoring the DNS time to lives. Then we move on to the right-hand side. We have first the Azure Application Gateway, and this is again a level 7 load balancing capabilities, meaning that you can do round-robin distribution of incoming traffic. We support cookie-based session affinity, again the URL path-based routing, and the ability to host multiple websites behind a single application gateway. And I can also name the advantage that by default, the application gateway can monitor the health of all the resources in its backend pool and automatically removes any resource considered unhealthy from the pool. And application gateway can also continues to monitor the unhealthy instances and add them back to the healthy backend pool once they become available and respond to health probes again, which is really cool. And last but not least, we have this simple but still powerful load balancer, the Azure Load Balancer. And this is an extremely high performance, low latency level 4 load balancing service for all the UDP and TCP protocols. It is built to handle millions of requests per second while still ensuring your solution is highly available. And Azure Load Balancer is zone redundant if that is a setup you're using so that you can ensure high availability across the different availability zones. Maybe the descriptions in the previous slide give you some light to guide you which load balancer you should use for your particular scenario. But I can also mention that you can actually use a combination of all the different load balancer to put them in the different places in your architecture. And this is just one example how you can do that. So in this case, we're actually mixing 3 of the load balancers that we discussed earlier on. So from the top, there we have a traffic manager that can decide which region the traffic should be routed to. And this is basically similar to the use case we used in the previous webinar. Maybe it is based on priority, await, or the actual network latency. The request is being either directed to region 1 or region 2. And when that request comes through, it will hit application gateway. And there you can use the URL path-based routing and see if the user should be actually directed to the images category or maybe the other request. And then finally, just between the web tier and the database tier, we are using a level 4 load balancer just to make sure that we distribute the load to the right database tier VMs. And it can also help to identify if all the VMs are healthy or if some of them need to be excluded. And lastly, in the fourth quadrant, I would like to introduce some of the HA capabilities that you can find built in some of the platform as a services offerings we have. So past services, I would say a lot of them come already with high availability built in. And services such as Azure SQL Database, Azure App Service, and Azure Service Bus, they all include high availability features and ensure that failures of an individual component of the service will be seamless to your application. And an example here is an article that let you read more deeply into how availability is achieved in Azure SQL Database. Using PaaS services, therefore, I would say is one of the best ways to ensure that your architecture is highly available. As a small summary, designing for high availability really helps keeping an application or process running despite unfavorable events and adverse conditions. But what do you do when something so significant happens that you've lost your data and it is impossible to keep your apps and processes from going down? With that said, I will shift the topic now to disaster recovery. Disaster recovery is about recovering from high impact events that result in downtime and data loss. A disaster is a single major event with an impact much larger and long lasting than the application can mitigate through the high availability portion of its design. And the word disaster often evokes thousands of natural disasters and external events. And there we can think about earthquakes, floods, tropical storms, and so on, depends on where you live. But many other kinds of disaster also exist. For example, a failed deployment or upgrade can leave an application in an unrecognized state. Malicious hackers, they can also encrypt or delete data and inflict other kinds of damage that keep an application offline or eliminate some of its functionality. Regardless of its cause, the best remedy for a disaster once it has occurred is a well-defined, tested disaster recovery plan and an application that actively supports disaster recovery efforts through its design. So in this process, as a first step, you should really create a disaster recovery plan. A disaster recovery plan is a single document that details the procedures that are required to recover from data loss and downtime caused by a disaster, and also identify who is in charge of directing those procedures. Operators should be able to use the plan as a manual to restore application connectivity and recover data after disaster occurs. The resulting written steps will promote good decision making and follow through in the chaos. Creating a disaster recovery plan is not easy either, and it definitely requires expert knowledge of the application's workflows, data, infrastructure, and dependencies. I'm going to introduce some common elements that is included in the disaster recovery plan. The first element that you definitely find is the risk assessment and process inventory. The first step in creating a disaster recovery plan is performing a risk analysis that examines the impact of different kinds of disasters on the application. Explore various kinds of hypothetical disasters and try to be specific when thinking about their effects. For example, a targeted malicious attack may modify code or data, and that impact is very different from a flooding event, which could disrupt network connectivity and data center availability. In addition, the risk assessment also needs to consider every process that can't afford unlimited downtime and every category of data that can't afford unlimited loss. When a disaster that affects multiple application components occurs, it's critical that the plan owners can use the plan to take a complete inventory of what needs attention and how to prioritize them. After that risk assessment and process inventory checkup, you will now move on to detailing what is your recovery objectives. A complete plan needs to specify two critical business requirements for each process implemented by the application. And these are the recovery point objective, also known as RPO, the maximum duration of acceptable data loss, and RTO, recovery time objective, which means the maximum duration of acceptable downtime, where downtime needs to be defined by your specification. We already talked about this in the first overview session, and here is actually a picture I think is really nicely drawn to illustrate what's the relationship between them. So RPO, as you can see, is the portion of the time where you have lost data before disaster happens, and then RTO is the acceptable downtime from the disaster happens until you actually put the system back to life. And note that each major process or workload that's implemented by an application should have separate RPO and RTO values. Even if you arrive at the same value for different processes, each one should be generated through a separate analysis that examines disaster scenario risks and potential recovery strategies for each respective process. So these are definitely not just arbitrary values, that these are looking good enough. And then as a last bullet point, you also need to detail recovery steps and each one of them. The final plan should go into detail about exactly what steps should be taken to restore lost data and application connectivity. And these steps often include information about backups, how often these are created, where they are located, and how to restore data from them. It should also include information of data replicas, including the number and locations of the replicas, the nature and consistency characteristics of the replicated data, and also how you can switch over to a different replica. Regarding deployments, how they're executed, how rollbacks occur, and failure scenarios for your deployments, what they are. Then regarding infrastructure, you should know your on-prem and cloud resources, your network infrastructure, and hardware inventory. External systems that are used by the application, including the SLAs and context information, such dependencies should also be included. And lastly, flags or options that can be set to gracefully degrade the application and services that are used to notify users of application impact, they should also be included as part of the scope. The exact steps that are required will definitely depend heavily on your implementation details, making it very important to keep the plan updated. The last advice is that routinely testing the plan will definitely help identify gaps and outdated sections. And continue on that note, disaster recovery plan doesn't end once you have completed your plan in hand. Testing the plan is a crucial aspect of disaster recovery, and you can really ensure that the directions and the explanations are clear and they're up to date. So basically, you want to know that your plan is working. And you should really choose intervals to perform different types and scopes of tests, such as testing backups and failover mechanism every month, and maybe performing a full-scale disaster recovery simulation every 6 months. You should always follow the steps and details exactly as they're documented in the plan and don't try to improvise. Consider having someone also unfamiliar with the plan will give the perspective on anything that could be made clearer. As you execute the test, identify gaps, areas of improvement, and places to automate and add these enhancements to your plan later on. And lastly, you can also make sure to include your monitoring system in your testing as well. For example, if your application supports automated failover, introduce failures in a dependency or other critical component to ensure that the application behaves correctly end to end, including direction of the failure and also triggering of the automated failover. With that, we also concluded the discussion around disaster recovery, and now we are entering the very last part, which is about backup. Well, I would say backup is the final and most powerful line of defense against permanent data loss. An effective backup strategy requires more than simply making copies of the data. As with disaster recovery strategy, backup requirements are based on a cost-benefit analysis as well. And this analysis of your application's data should be guided by the relative importance of the different categories of data the application manages, as well as external requirements, of course, such as data retention laws that you have to be compliant with. In order to establish backup requirements for your application, you should try to group your application's data based on the following requirements. How much of this type of data can really afford to be lost, measured in duration of time? What is the maximum amount of time a restore of this data should actually require? And then also backup retention requirements, how long and what frequency you should do the backups to make the data available. This concept maps neatly to the concept of recovery point objective and recovery time objective, and this is definitely not just a coincidence. The duration of acceptable loss will generally translate directly to required backup intervals and RPO. The maximum amount of time a restore takes corresponds to the RTO for the data component of your application. A customer would probably like to say that they can't afford any single data loss, but we also know that reality often is not the case when the cost of achieving that requirement is considerable. Other than to support disaster recovery, backup can also be used if a small amount of data older than your backup interval is corrupted or deleted. So in this case, even the application doesn't experience any downtime, the functional correctness of application can depend on the data quality. And backup is another very efficient procedure to bring that back. And here I have a really good tip. I know that many people, once they learn a lot of different concepts about disaster recovery, backup, high availability, and so on, they get confused by some of these terminologies that we use. And yeah, and I can totally understand why. So that's why I think it would be useful to do a short summary of some of the terms that people get confused about. So first we have Archival, and that is the storage of data for long-term preservation and read access. Remember, this is the lowest tier of all the three available ones you have in the blob storage. Then we have replication and backup. I would say these two are usually where the main confusion lies. Replication is really about near real-time copying of data between your replicas to support a high availability and certain disaster recovery scenarios. And you also have backup, which is to save the state of an entire system and do so at regular time intervals. And this is not really highlighting the property of near real time. Some of the requirements I would say, such as data retention laws, they might influence your strategies for all of these different concerns, archival, replication, backup, but you still require separate analysis and implementation to meet the requirement of each one of them. And next, I also want to walk you through some of the typical Azure backup and restore capabilities that you can browse into when you are choosing a good backup solution for your workload. So basically, Azure offers several backup-related services, including data in Azure as well as on-prem data. Most Azure services offer some kind of backup functionality, and here we'll look at a few of the most popular backup-related Azure offerings. The first one, we definitely have to mention Azure Backup. This is a family of backup products that back up data to Azure Recovery Service Vault for storage and recovery. Recovery Service Vaults, they are storage resources in Azure that are dedicated to holding data and configuration backup for your virtual machines, your servers, and also individual workstations and workloads. For example, one of the members in the family, Azure Backup Agent, is a small Windows application that can be used to back up files, folders, and system state from the Windows VM or server on which it's installed. It works in a way that's similar to many consumer cloud-based backup solutions, but requires configuration of an Azure Recovery Vault. Once you download and install it onto a Windows Server or VM, you can configure it to create backups up to 3 times a day. Azure Backup serves as a general-purpose backup solution for cloud and on-prem workloads that run on VMs or physical servers. It's designed to be a drop-in replacement for traditional backup solutions that stores data in Azure instead of archived tapes or other local physical media. Then we have Azure Blob Storage. Well, technically, the Azure storage doesn't include an automated backup feature, but the blobs are commonly used to back up all kinds of data from various scenarios. And many services that provide backup capabilities, they actually use blobs to store their data. And blobs are a common target for scripts and tools in every kind of backup scenario. And again, a quick review, the general purpose V2 storage accounts support 3 different blob storage tiers of varying performance and cost. We have the cool storage tier, which offers the best cost to performance ratio for most backups, as opposed to the hot tier, which offers lower access costs but higher storage costs. The archive tier storage may be appropriate for secondary backups or backup data with very low expectations for recovery time. And here I can also mention that the immutable blob storage is configurable to be non-erasable and non-modifiable for user-specified interval. And this immutable blob storage was designed primarily to fulfill strict requirements for certain kinds of data, such as the financial data. And it's definitely a great option for ensuring that backups are protected against accidental deletion or modification. Then we have the Azure SQL database, in which you can find very comprehensive and automatic backup functionality at no extra cost. And full backups here are created weekly, with differential backups performed every 12 hours, and log backups are created every 5 minutes. Finally, we have the Azure App Service. The web applications hosted in Azure Web Service standard and premium tiers support turnkey scheduled and manual backups. Backups include configuration and file content, as well as contents of databases used by the app. They also support simple filters for example, excluding the files. Restore operations can target different app service instances and making app service backup a simple way to move one app's contents to another. All right, and last note, no backup system is complete without the strategy for verifying backups and testing restore procedures. Even if you use a dedicated backup service or product, you should still document and practice recovery procedures to ensure that they are well understood and return the system to the expected state as you desire. Strategies for verifying backups, they can look very different and it will depend on the nature of your environment as well. You may want to consider techniques such as creating a new deployment of the application, restoring the backup to it, and then comparing the state of the two instances to verify if the backup is successful or not. In many cases, this technique closely mimics actual disaster recovery procedures, and simply performing a comparison of a subset of the backup data with the live data immediately after creating a backup is also a good enough approach. A common component of backup verification is attempting to restore all backups to ensure that they are still available and operational, and that the backup system hasn't really changed in a way that renders them incompatible. And now again, we are in the very end, the summary slide. We have discussed some key principles of the reliability pillar of the Azure Well architecture framework. You have seen how you can make your application available and recoverable by architecting for high availability, disaster recovery, as well as backups. We start by looking at how to use availability sets and availability zones on Azure to provide high availability for your VM workloads. We also looked at what are the different load balancing services such as Azure Traffic Manager, Azure Application Gateway, and Azure Load Balancer to distribute load across available systems. PaaS services, on the other hand, have HA already built in, so leverage these services to architecture whenever possible. Then we also look at disaster recovery regarding how to define your RPO and RTO of your application and how to design data as well as process recovery. We also learned that incorporating backup and restore into your recovery strategy for protection for isolated data loss scenarios. And finally, we also explore what are the typical backup solutions that are available on Azure to suit different scenarios. And as usual, I prepare some resources for you. The first link there, you get a long list of service level agreements of the different services that Microsoft actually promised to the end users. And then we also have some deep dive documentation links if you want to read more into the Azure regions and the availability zones, how you can use Azure site recovery to prevent regional level disaster, and the load balancer options. So here you have a more comprehensive guide, what are the different options and how and when you should choose which to use. And finally, we also have a deep dive article on Azure Backup. All right, and now again in the Q&A corner. And today I prepared two questions. The first question is, how will the availability zones and set concept be mapped in the new Swedish data center? Well, to clarify, so first of all, Sweden by itself will be a new geo. And then underneath that, we have a region called Swedish Central, which is composed of a number of different sites in Gävle and Sandviken. And there will be 3 different availability zones that you can utilize. And availability sets are definitely supported as they only require the workloads to be placed on different fault and update domains in a particular site. The next question is, do we really need both backup and disaster recovery simultaneously? Well, this question is semi-answered by the comparison chart I showed you earlier on. What's really the difference between backup and disaster recovery? I can also now highlight that the purpose, what's the purpose they are trying to achieve. The replication really is trying to ensure continuous access to your mission critical and customer facing applications, while backup is really focusing on long-term data storage and compliance related requirements. It can also solve the case of data loss or corruption, which is essentially not in the scope of disaster recovery, but it is one of the advantages that you can utilize backup for. So with that said, again, thank you very much for listening. And in the next session, we will cover together the very last pillar in the Azure Well Architecture framework, which is security. Thank you for today. Stay tuned. See you next time.